This week, we'll pay attention to two main problems of multiplication: multiplication of numbers and multiplication of matrices. And we have already studied multiplication from the point of view of circuit complexity. So we have designed circuits that are able to multiply numbers in the binary representation. For n bit numbers, we had circuits of depth big O of logarithm of n, and the complexity of the circuit was quadratic. So the number of gates was big O of n squared. Now, this week we'll study bit complexity on a software model, on a RAM model. We'll not talk about gates and circuits and wiring these gates. We'll talk about like standard algorithm. You can assume that this algorithm is written in standard programming language, but we are counting each operation on bits of input numbers. This is called the study of bit complexity. So we start with bit complexity of multiplication for integer numbers. So take two numbers given in their binary form, a and b. Both of these representations are in binary. Now, if we use just standard schoolbook method for multiplying these two numbers, we just take the first of them and multiply by the rightmost bit of the second number, so we get a large string of bits like this. Now we multiply the first number by the next bits of the second number, and so on. So thus we get a ladder of numbers that we, of course, pad from the right with zeros, and we then add them up. But actually the bit complexity is already spoiled by this part. So just to compute and to consider all these pairwise products, conjunctions of bits, we spare quadratic complexity. So we have theta of n squared operations here already at this step before we even try to add these numbers. When we talked about circuit complexity of multiplication of numbers, it was not a great deal that we had these n squared operations here, because all these conjunctions can be computed at once in a single layer of the circuit. And so this takes like 1 unit of time. But now we turned to a model when each operation counts on its own. So it either corresponds to the size of the circuit or corresponds to just a program running on a single threaded processor. So we'll try to do it better than with theta of n squared operations. So let's try divide and conquer approach here, one of the standard approaches in computer science, and see what it can do for us here. The simplest way that we can try to apply divide and conquer is to divide each of the numbers that we have in two halves. We say that A really consists of two halves of this binary representation, from a n minus 1 through a n over 2, and then a n over 2 minus 1 through a0. And these two halves correspond to two numbers in binary notation. The one a1, the second will be a0. So each of these numbers, a0 and a1, is an n over 2 bit number. Now, the same we do with number b. So we divide its binary notation into two halves, and we call the number which corresponds to the first half by b1, and the number corresponding to the second half by b0. Arithmetically, we can now express a through a0 and a1 as a0 plus 2 to the power of n over 2 a1. And the same goes for b. We see that we do not place any floor function on CD function on n over 2, and indeed we can assume that n is just the power of 2, so that we can divide n by 2 and recursively proceed with division on any level that we like, because if our numbers a and b have length which is between powers of 2, say 2 to m and 2 to m plus 1, then we can always pad our numbers with zeros. So consider just numbers like these, and the length of these numbers would be 2 to the power of m plus 1. So if we denote this by capital N. Now this capital N will be the power of 2, and if we get any bound on the time complexity of our algorithm, the number of bit operations for multiplying these numbers, so if we get, say, the bound like T of n is big O capital N to the power of C, where C is some constant, then T of n is big O of 2n to the power of C, because we know that capital N is less than 2n, and this in the end is just the same as big O of n to the power of C. So it doesn't matter with what numbers to work, with general kind of numbers or with just numbers that are powers of 2. And we'll assume what is more convenient for us, so that we have already padded our A and B so that their length is a power of 2. So now let's try to employ divide and conquer and express the product of A and B through these numbers, through the parts of A and B. So we see that the product of A and B is A0 times B0 plus 2 to the power of n over 2 times A0 B1 plus A1 B0 plus 2 to the power of n A1 B1. So we see that we have some number of additions. Also, we have multiplications by some power of 2, but that's just padding right with zeros. So this operation is not a decent multiplication. And the number of actual multiplication of numbers that we need to do here is 4. So we need to perform these 4 multiplications, compute these products. Thus, we can express the bound for our complexity of the algorithm for n as 4 times the complexity of multiplying n over 2-bit numbers, because each of these products is a product of n over 2-bit numbers, and plus big O of n, because addition, subtraction can be done in linear time. We have already considered circuits for the circuit complexity, but all that can be easily translated into standard algorithmic bit complexity. Unfortunately, for this kind of bound, the master theorem allows us to enroll it only as T of n, as big O of n to the power of log 2, 4. So these 2 comes from here. This is the size of our subtask, and these 4 comes from here, the number of the subtasks that we recursively solve using our algorithm. So this is just quadratic complexity again. So actually, for now, divide and conquer was of no use. We got the same quadratic complexity as we did using just school book method. But at least we see where we can improve. So if we like to fruitfully use divide and conquer approach in here, we cannot improve this guy, but we can try to improve this guy and try to place, say, 3 instead of 4. And to do so, we need to improve it here. So we do not need to compute 4 products of n over 2-bit numbers. We have somehow to compute just 3 such products. Now, the idea of Karatsuba and Ofman was precisely this one. The idea was to compute A0 times B0, to compute A1 times B1, and then to compute this guy as a whole by means of the following formula: A0 plus A1 times B0 plus B1, and minus what we already have computed, A0 times B0 and minus A1 times B1. So to compute all the ingredients of the formula, we need 1, 2 products and 3 products. All the other things here are additions, subtractions, which we already know how to perform in linear time. The only detail here is that this is the product not exactly of n over 2-bit numbers, but these numbers A0 plus A1 and B0 plus B1 are actually n over 2 plus 1-bit numbers, because we could have carry while adding these numbers into the most significant bit. But if we write down these sums as, say, C, capital C, where this guy is a binary number of n over 2 bits, and this is additional bits that can happen here. And if we write down this number as D, capital D, again, where capital D is a binary number with exactly n over 2 bits, we can see that we can multiply these two numbers like this: C capital C times D capital D, 2 to the power of n C D. This is just a product of 2 bits padded properly, plus 2 to the power of n over 2 C times D plus D times capital C, and plus C times D. So this is a product of two n over 2 bit numbers, so we need T of n over 2 operations to compute it. Now this is a product of a single bit by a number. This is also a product of a single bit by a number. This is just padding. This is 1 bit padded properly. We have addition here. So everything that we have here is doable in big O of n time. So in the end, this thing can be computed in T of n over 2 plus big O of n time. This thing can be computed in T of n over 2 time, as well as A0 times B0. And we indeed have just 3 recursive calls to our algorithm, plus some time which is linear on n. And in the end, indeed, master theorem will tell us that the time complexity of our algorithm, T of n, is big O of n to the power of log 2, 3, which is subquadratic. Now the question is, can we further improve that? So can we split our numbers into 3 parts or 4 parts, and then using some clever formulas, can recombine these parts so that we get all the ingredients to construct the product of the numbers? And indeed we can do so, and we'll learn that while discussing Tolom's algorithm. So actually, this exponent that we have here can be made as close to 1 as needed. Of course, at the expense of a very large constant in this big O. So these algorithms tend to be not very practical, but theoretically it's doable. And we'll learn how to do it a bit later. Now we'll discuss, as our next application of this idea and divide and conquer, the matrix multiplication, our first algorithm for working with matrices.